So, alrighty. We are going to segue in this unit, finally stop talking about individual atoms and elements and stuff, although you have to remember all that for your test. Honestly, all that we covered in Unit 1 about atoms, atomic structure, elements, the periodic table, molar mass, blah, 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 you need to know that for the whole course. But kind of building on that, we're going to be talking about compounds. So just bear with me if I get excited. Compounds are fun, right? So remember, this is kind of probably a review slide from back in Unit 1 when we talked about compounds in general. They are another type of pure substance, and compounds have a set formula that can describe them. H2O is the formula for the compound water. My daughter at the eye doctor the other day, she's like, so is there another name for water? And she was just asking all, she's taking chemistry in high school. So we talked about nomenclature. But the thing about compounds is they can be broken back down into their elements. So if we have pure substances, ooh, goodness, I didn't change that color. And we said there's two types of pure substances. There are elements, and then there are your compounds. And I abbreviate compounds CPD, and you can go back and forth with some sort of chemical reaction. So I abbreviate chemical reaction CHM165 Okay. So that's to say that elements can be assembled via chemical reaction to make a compound, and a compound can be broken down into atoms of its assorted elements via another chemical reaction. So I think we've seen this one, but actually I don't have this one queued up. I'll try it, but if it doesn't play, I'm not too freaked out. No, just kidding. So I like this video. It looks like it's trying to play. This is the video that takes a compound, mercury oxide, via flame, breaks it down into cute little oxygen atoms, take off, and you're left with little mercury atoms. Which is kind of the opposite of what you did Thursday. What did you do Thursday? Okay. I didn't think this could go. What you guys did Thursday was to take cute little magnesium atoms and add oxygen to it and end up with a compound, right? So that's kind of the opposite of that. So you guys have dabbled in chemistry before. You're familiar with this idea of a chemical formula to represent a compound that tells you how many atoms of each type of element there are in that repeating unit. Whether that's, and I'm going to remind you, two types of compounds. There are molecular compounds, and then there are ionic compounds. And we're going to hit that in this unit of material. So one of the things, just to kind of remind you so we're all on the same page, is that, for instance, if we have, let's pick on this one, magnesium nitrate. That means that things that are in the parentheses, this parenthesis outside, wait, how do I say this? That number outside the parentheses means you need two of those. Okay, so this one actually is magnesium, and it's kind of got two NO3 groups. Okay, like that. So how many oxygen atoms do you have? 6, that's right. So those are my nitrate groups. That's my magnesium. Now here we're going to talk about chemical bonds that attach, that makes atoms stuck together. Okay, there's two types of chemical bonds. There's covalent bonds. You're going to see me draw them with just a solid line like that. And then there are ionic bonds, and I draw my ionic bonds with a dash, 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 dash. So some of you are familiar. We'll be talking more about this, but I'm going to put dashes between that central magnesium atom and those two nitrate groups. Alrighty. Okay, so this is kind of the first, yeah, go ahead.
Is it okay if we, well, I was taught to just put one pot for ionic.
Probably. It's kind of a visual convention.
That's just the way,
Yeah. So we'll be hitting hard the difference between the two molecular, the two types of compounds. one of the things, the theme of describing the two compounds is that if you're talking about a molecular compound, you'll talk about the repeating unit as a molecule. If you're talking about ionic compound, you're going to talk about the repeating unit as a formula unit. So that's a big thing. You kind of know your chemists from your non-chemists. If, for instance, they talk about a molecule of salt. You're like, okay. Okay then, what school did you go? No, I'm just kidding. Okay, because salt is an example of an ionic compound. And the repeating unit would be a formula unit. Okay, so. But I guess with that said, all kidding aside, we use this term molecule kind of just when we probably shouldn't out there in real space. Okay, so these, the methane, ammonia, and water, all of those compounds, and you see the formulas for those compounds are all molecular compounds. And I'll give you a quick and dirty check for if the formula represents a molecular compound or not. Did you have a question? Okay. So the cool thing about molecular compounds exists as molecules, and it's kind of like, you know, when you go to a magic show and the magician appears to make somebody hover in space, okay? So my thing about molecules is you could take your hand and go all the way around and say it's a molecule. And you could go all the way around here. Are you really that tired, Matthew? And make it a molecule, okay? Not so much with ionic compounds that exist in their solid state. So we use formulas to represent the atoms that are in the repeating unit of a molecule or a formula unit. Okay, so we're going to talk about different types of ways of expressing the formula. This is the molecular formula for acetic acid. Not much information there. We can get more. We can do better than that. As some of you guys know, formulas for molecules or molecular compounds like acetic acid can be broken down into their empirical formula. I'll just kind of give you a hint here. Do you see where if we go with C2H4O2, if we divide the 2 and the 4 and the 2 by 2, we get CH2O. We have the same relative numbers of atoms of carbon, hydrogen, oxygen in both those formulas. We say the empirical formula is a reduced formula of the molecular formula. So we'll be talking more about that later. So here's a structural formula. It gives a lot more information. Okay. So the structural formula, for instance, we have a couple of functional groups here. We have the hydroxide group and we have the acetate group. Okay, we can give spatial representation of acetic acid. Okay, so I told you that water is an example of a molecular compound. So molecular compounds have the repeating unit of a molecule, and molecules are basically kind of independent of their fellow brethren. Okay, this is to say that for this Mickey Mouse, upside down Mickey Mouse molecule, okay, H2O, we know it's one oxygen and these two hydrogens go together. So now these are queued up. We might have seen them before. So switching gears to ionic compounds, there are some differences. (1001), 1002. What did it say? Oh, okay. Now I'm probably going to get 10 billion instances. Down here. There they go. 10 billion instances. We'll pick one.
When sodium and chlorine react, the sodium transfers an electron to the chlorine. forming oppositely charged ions. Although the compound has no net charge, its component ions of opposite charge attract each other to form ionic bonds. In turn, these ions are attracted to others, and an ionic solid called a crystal lattice is created. When sodium and chlorine react, the sodium transfers and...
Okay, so the thing about it, well, a few things. In its solid state, you can't be like the magician and basically take your hand and circle those chlorine, those big chlorine things. The green things are big chlorine atoms or ions, picked up an electron. The little ones are sodium cations that's lost an electron. And you have a dot between them, or a dot, dot, dot. Those gray things are the ionic bonds that connect them. So you're kind of like, this is called a crystalline lattice. Okay, so that's one characteristic of ionic compounds in their solid state. Oh, it's working. Alrighty, and it's Monday. Okay, so we could say, and you have a slide coming up, if you pick any, let's pick that one right in there. If we pick that particular chloride ion, and you go up and down and over and over and over and over, it's actually connected to 6. Okay, it's connected to 6 different cations. So it's like a community. Let's see. This one should play for us too. So sodium chloride is an example of an ionic compound. So is, I think this is sodium bromide.
A crystal of potassium bromide has a distinctive shape with perpendicular edges. This shape directly reflects the arrangement of the ions in the crystal lattice. The compound is composed of alternating potassium ions and bromide ions.
Your solid state crystalline lattice structures. Okay, so this is just a still image from your textbook, kind of showing you. And ionic compounds then have these kind of smooth surfaces, and they're kind of breaking off and showing you kind of the face of the crystalline lattice structure. So here's a slide. I think we did this slide before. Again, back in Unit 1, if it sounds familiar, it's because it is. But we're going to further dive into making sure we know the difference between an ionic compound and a molecular compound. Okay. So down here at the bottom, it says there is no family unit. And that means, like, for instance, for a water molecule, you know which oxygen goes with which 2 hydrogens. With this one, not quite so sure. So here, this is a very good hint, okay? Because one of the things you should be able to do is to look at a formula of a compound and tell me which kind it is. So you just basically look for your metals, okay? If you have a metal at all, then you are dealing with an ionic compound. And just to kind of remind you how metals go, here's my this is my rendition of a periodic table. Isn't that terrible? Oh my gosh, that's not too bad. Okay, and then we have a jag right here, and I should be counting my stair steps. Okay, but where are the metals there? They are on the left. Very good. These are all metals. So in general, if you have one of those, it's an ionic compound. Okay. So here's the deal then. This goes on to say, and I kind of hinted at this before, these guys right up here are nonmetals. And they are a lot of important players with regard to life. Okay, look at the nitrogen, oxygen, phosphorus, those are, and hydrogen. Remember, I put hydrogen both over here and over here. I did that on purpose. So look for a metal. If there's metal in your formula, then it's an ionic compound. Basically, yeah.
What about metals with metals?
Metals with metals, it doesn't happen.
Doesn't happen.
Yeah. You think it happens all the time when you have like steel, you know, but what you have when you have like stainless steel with different amounts of, depending upon what grade of stainless steel you got, you have a solid solution. It's an awesome sort of thing. It's a homogeneous, frozen in time set of metal atoms that are just frozen together. Yeah, and electrons flow in that a sea of electrons. But yeah, good question. And the other thing, I guess I would go back to, have hydrogen up there twice. This is where I usually tell students hydrogen, for all intensive purposes, is a non-metal. Non-starter, no. Hydrogen is a non-metal. I would say, what percent of the time? Maybe 90%. 90% of the time. Hydrogen is non-metal. So when we look at H2O, and don't be shy to find oxygen on the periodic table. Sometimes students are like, I don't know if these are metals or not. Well, look at the periodic table. So, of course, we find oxygen in that kind of little triangle. That's a nonmetal. Hydrogen, I said, is a nonmetal. No metals, must be a molecular compound. Sodium chloride. Okay. So you're like, I don't know. Well, find a periodic table. They're all over the place. Okay. So, of course, sodium is in that bank of majority of elements called a metal, right? So, dang, it's an ionic compound. All right. So this works really, this aspect of Unit 2, actually most of Unit 2 works really good with Unit 1. Because in Unit 1, one of the things we did was talk about that decimal number for the elements. And we said that's an average weight for an atom of that type of element. So if you want to get a weight for a molecule, you just add them up, okay? So it's not too bad. Notice units of molecular weight will be atomic mass units. So it usually works pretty good. So we have an example here. Oh, before I have an example. This might be a deja vu slide. Wait, molecular weight, formula weight. What gives? Well, we have to differentiate between the two types of compounds because we call molecular compounds molecules, molecular weight. We call ionic compounds, repeating unit, formula units. So formula weight. So I said hydrogen is a nonmetal for all intensive purposes. Nitrogen, if you don't know, find it on the periodic table. I still have to. Nonmetal. So hydrogen, nonmetal, nitrogen, nonmetal. This is an example of a molecular compound. So when we find the mass of the repeating unit, it's going to be a molecular weight instead of a formula weight. Okay. So without belaboring the builds, okay, you wouldn't have to, of course, put the pink stuff down here. But kind of from left to right, you need to look at each element in your compound. Okay, you need, the whole numbers represent how many of that atoms of that type of element there are. Okay, so there's 2 nitrogen atoms. The decimal number for nitrogen is 14.01. There are 4 hydrogen atoms. And I'm going to give you a rule of thumb, but your periodic table, since hydrogen is so light, ought to have given you 3 decimals instead of just 2 decimals. Okay, so for that hydrogen, each hydrogen will weigh 1.008 atomic mass units. So you add that out, and if it's relatively heavy, above 10 AMUs, the weight of this molecule, you're going to round it to 2 decimals. Okay, so hydrazine weighs 32.05 atomic mass units. That's its molecular weight. See, I don't see anybody sweating out there. I'm sure you guys are good with this. Now, for calcium nitrate, it's similar, but it's not a molecular weight. It's a formula weight. Why? Because it is an ionic compound. Why is this an ionic compound? Can you tell? It's a metal. Yeah, calcium's a metal. So here, the only catch is you need to make sure that you distribute that 2 that's outside the parentheses of the nitrate, you need to distribute that through. So of course you have 2 nitrogens and 6 oxygens. Okay, but otherwise it's very similar. You know, here, notice that I'm explicitly showing the 1 times the mass of a calcium atom because I want to show that, yes, I did check. There was 1 calcium. Its decimal number is 40.08 AMUs. Plus there are 2 nitrogens. They each weigh 14.01 AMUs. And there are 6 oxygens. See? Not too bad. But there are programs out there on the internet that you can, you know, if you're in a hurry trying to do a calculation and you need the molecular weight or the formula weight or the molar mass, you can type in the formula and it will spit it out. Of course, for your homework, you have to show me this, though. Let me go ahead and say that. Show all work. In fact, the reason I'm including that on this slide, W-O-R-K, work. Show all work, because a lot of times students will tap this into their calculator and they'll throw it down. And you may be right or you may be wrong. But you'll lose points. Okay? Like, why? Because I said, part of what I'm trying to do is get you ready for engineering, going on, you know, staying in the sciences, and you really can't just be you really have to be writing down your thoughts. And part of writing down your thoughts is writing down what you put in the calculator. You're communicating. Okay? So, yeah, you need to show all of your work in order to get full credit. Okay. Deja vu? Seems like we just covered this in Unit 1. Okay, we covered an important thing in chemistry is the molar mass. And we said that is, if you want to get 1 mole of atoms of a particular type of element together, okay, we can tell you what the molar mass is. We said you need to look at the decimal number. Okay? And there are times, quite frankly, when you don't want 1 mole of hydrogen atoms, you want 1 mole of water molecules. You have to scale it up, right? We're going to find out that the molar mass of water is going to be the same number as the molecular weight of water, but instead of AMUs, it's going to be grams per mole. So the magnitude of the number, it's numerically equivalent to what we were just talking about, the weights. But the weights we said were in AMUs, molar mass is in grams per mole. Okay? So last unit, we said that if you want to know what the molar mass of an element is, you look at its average atomic weight. Okay, here, for these 2 types of compounds, if you want to know what the molar mass is for a molecular compound or an ionic compound, you knock out its molecular weight or its formula weight, respectively. Okay? And then you doctor up the units from AMUs to grams per mole, and voila! You have it. The molar mass of water, the molar mass of calcium nitrate, the molar mass of hydrazine. Okay. And just like we did problems before, if you know the molar mass of anything, you can use it to go back and forth between grams and moles of that particular thing. Now, it's not going to be atoms, it's going to be formula units or molecules. All right. So before we do a conversion problem, let's just say somebody asked you you're given these 2 compounds and asked you to come up with the molar mass for these 2 compounds. Don't use it as a conversion factor, the molar mass, but just tell me how many grams you need to set aside to get 1 mole of those compounds. Well, you would start out by basically doing molecular weight and a formula weight, respectively. Notice I put the word explicit up here. You can jot this down if you want, but I'm going to show you a short, let's see, how do I say it? I'm going to show you a streamlined Dang it. Streamlined way to show this problem here in a minute. I would not explicitly do it like this. It's too much work. But say somebody gave us the formula of this compound, C2H6, and said, what is its molar mass? Well, I'm going to come up with its, basically going to do a problem very similar to what I would do for its molecular weight. I'm going to recognize that those little subscripts, 2 and 6, mean that we have 2 moles of carbon for every 1 mole of compound. And I know that the molar mass of carbon is the decimal number for carbon, 12.01 grams per 1 mole. That's my carbon term. And then I got to account for my hydrogen, and the subscript is 6, so I put there are 6 moles of hydrogen for 1 mole of C2H6 molecules. The decimal number for hydrogen is 1.008. There are 1.008 grams of hydrogen for 1 mole of hydrogen. Okay? You're going to like the shortcut. Wait a minute. Then we just need to make sure, since somebody wanted, they didn't want molecular weight, they wanted molar mass. And one of the things, the units of molar mass is grams, in this case is C2H6 per 1 mole of C2H6. All right. The streamlined or abbreviated calculation goes like this. You account for the carbon term, you account for the hydrogen term, you write down what your calculator displays, you round to 2 decimals. Much better. Do you think you have to include your units on the end? Yeah. Did I include any units, though, in the problem? No, I didn't. This is one of the times when I don't. Notice there aren't any units here. I just kind of, but do I show my work? Yes. Yeah, there's no units here. Okay, I'm just taking the decimal number for carbon, the decimal number for hydrogen, multiplying them each by whatever the subscripts there are in the formula, coming up with my answer, and since it's molar mass, it's grams per mole. Much better. So let's knock out ammonium chloride. Now remember I said that hydrogen, what did I say about hydrogen with regard to being a metal or non-metal?
Non-metal 90% of the time?
I did, said it was a non-metal 90% of the time. This is an example where anytime you see this little critter here, okay, that is ammonium. And that is NH4 running around with a +1 charge. Okay, so the thing about this is all a long way to say, is anytime you see ammonium, that must be acting as what we call a polyatomic cation, and that must mean that you have an ionic compound. All rules were meant to be broken. Okay. So you'll have some practice. Ammonium is a kind of a common polyatomic cation in kind of reactions that we look at. So it's an ionic compound, so I wouldn't find a molecular weight. I would find a formula weight, but let me go ahead and show you the abbreviated way. Account for the nitrogen. There's 1 of them. It weighs 14.01. Account for the 4 hydrogens, part of ammonium, 4 times the decimal number for hydrogen, 1.008. And the chlorine is getting kind of heavy there. Its decimal number is 35.45. I just go ahead and I would round to 2 decimals, whatever my calculator displayed, because it would give me a 3rd decimal, because that hydrogen is kind of tagging along there. 53.49 grams per mole, the molar mass of that compound. Not too bad. So this is what I've been kind of saying, is that I've used light, if you have something kind of light, okay, like something less than 10 AMUs, okay, you need to go ahead and give 3 decimals in general. Okay, otherwise, everything else 2 decimals. Cool. I think that is how far I wanted to get to today. So remember all that we've talked about. And on Wednesday, we'll knock out this part, and so there will be an assignment that's due Friday. Anytime. No assignment for Wednesday. I'm okay, thank you. Thanks for asking.
Maybe that rain was a good thing. Yeah.
Oh, quit. But I'll go grab those things off the computer, or off the printer.